Okay, so today I want to talk about the Higgs boson. And the reason I want to talk about this is because I feel like I hear it thrown around a lot, but I don't feel like really too many people actually know what it is. I just hear it thrown around a lot. Maybe people want to make something sound complicated, use some kind of complex analogy for whatever reason. But I don't think too many people actually know what it is, what it does. It kind of reminds me of like how everybody kind of says and knows about this saying, oh, the mitochondria is the powerhouse of the cell. But does anybody really know what the mitochondria is? Well, it's the powerhouse of the cell, but do they know much more about it than that? I don't really think so. It's just kind of one of those things that people say. And I feel like it's kind of similar with this Higgs boson. And so that's why I want to talk about it today. And what it is it comes out of the question, like, where does mass come from? Now you could say, oh, well, mass, it comes from, atoms, right? So if you look at, for example, helium, it's got two electrons, and it has two protons and two neutrons. So, you might say, oh, well, the mass comes from, the electrons, you add up the electrons, you add up all the protons, all the neutrons, and then that's the mass, right? And, well, yeah, it's absolutely true, but where do those particles get their mass from? The electron, it's already an elementary particle, so you can't go down any further than that. But for the proton and the neutron, those are not elementary particles, and they are each made out of 3 quarks. Pretty much like every particle that's not, made up of another, that's like not an elementary particle, it's going to be made up of 3 quarks. Now, let's say this is the neutron here, and then this is the proton. The charges are going to have to add up, to being positive, right? So you got the 2 positive ones, the 1 negative one, 2 positives plus 1 negative equals 1 positive. So there you go. You got the proton with the positive charge. This electron has a negative charge, The neutron doesn't have a charge, though. It's neutral. So how can, if there's an odd number of quarks, how can it come out to 0 charge? Well, you just gotta balance the charges. And what I mean by this is, so this would be 1 divided by 3, and 1 divided by 3, and 2 divided by 3. 1 plus 1, 2, 2/3 cancels out, equals 0. And where the charges come from is it has to do with the spin. So another word for a positive quark is an up quark, and for negative, it's a down quark. What does up and down mean? What do those words have to do with anything? Well, again, it has to do with the spin. So you do the right hand rule. Positive is always up, out of the page. Negative is down this way. So if the cork is spinning this way, it's down. And this way, it's positive. So that's where the charges come from. And then the intensity of the charge is like how fast it's spinning. But okay, where do the quarks get their charges, get their mass from? You know, where do the quarks get their mass from? Well, most of it comes from the gluonic force. Now that kind of sounds a little confusing. Like, how could a force equal a mass? But then you gotta remember the E equals mc squared formula. The reason this formula comes in handy for this is because energy and mass have a relationship. So if you have mass, you have energy, and if you have energy, you have mass. So in this case, the energy is the energy required to make this force that holds the quarks together. And since this c is the speed of light and it's squared, the mass needs to be really, really small. And the energy is going to be very, very big. And so just a very, very little amount of mass is going to make a lot of energy. And so if you think proportionally, if most of the mass is coming from this energy, this force that is holding the quarks together, there must be a lot of energy, relatively speaking. And maybe if you think about it, you can make it make sense. For me, I think about how much, increasing amount of energy it requires for me to push two magnets together with the same charge. It gets really, really intense as you get very close. And you think at this scale, how close it is. So most of the energy comes from the gluonic force. About 90% or so, maybe even more. But what about that remaining 10%? Well, the remaining 10%, this is where the Higgs boson comes into play. And what it is it's the quark passing through a bunch of Higgs bosons. And this kind of cluster of Higgs bosons is called the Higgs field. So, you imagine this quark is moving to the right through this Higgs field, and the Higgs field is everywhere. Everywhere there are Higgs bosons. And everywhere there are elementary particles like this quark passing through it. And what the Higgs field is doing is it's imparting a drag on this quark. You think of you pass your hand through water, through a swimming pool, and it's a lot harder to move your hand. And so the mass comes from the drag of the particle moving through the Higgs field. And all these little dots are little Higgs bosons. So that's it, man. If you could subscribe, that'd be pretty sick. This red color represents the subscribe button. So if you don't see this red button or this red color, you're good. If not, you gotta make sure you click that. Otherwise, I'm gonna come to your house and you don't know the stuff I know about this quantum mechanics. You don't know how I'm gonna be able to use that to get ya. So you better hit that subscribe button.